In Chapter 3, we'll take a look at initializing the part, how to work with the GPIO, and our first look at TivaWare. TivaWare for C-Series is a license and royalty-free set of code for TI Cortex-M devices. It includes the peripheral driver library, USB stacks, Ethernet stacks, graphics library, sensor library, extensive examples, and some additional features. The libraries are available as object and source code. The peripheral driver library is a high-level API interface to the complete peripheral set. The source code also demonstrates good programming practices should you need to program registers directly. The peripheral driver library is programmed into the on-chip ROM of all Tiva C-Series devices. Tiva C-Series devices are USB device and embedded host compliant. Device, host, on-the-go, and Windows side examples are available. TI has a free vendor ID, product ID sharing program should you wish to use it. Ethernet is supported with lightweight IP and micro IP open source stacks. Both stacks have been modified to support the IEEE 1588 Precision Time Protocol. The graphics library includes primitives for drawing shapes, text, and images on the screen and widgets to tie touchscreen buttons to in-program actions. The library has 153 fonts plus Asian and Cyrillic support. Also included are graphics utility tools for converting files and making customized button graphics. The sensor library includes drivers for I2C and the sensors that you'll find on the Sensor Hub Booster Pack. Examples and a set of common routines for sensor operation are also included. In the extras category, we have the Simplicity Wireless Protocol, IQ Math examples, bootloaders, and additional Windows side examples. The bootloader is preloaded in ROM, or it can be programmed at the beginning of Flash to act as an application loader. You can also use it as an update mechanism for an application running on a Tiva microcontroller. This technique is called paging. The bootloader can boot through the UART, SSI, I2C, CAN, Ethernet, or USB ports. Since full source code is provided, the bootloader can be completely customized. There are 4 fundamental clock sources on Tiva C-Series devices, which offer the developer very flexible choices when clocking the device. The Precision Internal Oscillator is a 16 MHz oscillator plus or minus 3%. No external oscillator or crystal is required. The main oscillator uses an external single-ended clock source or an external crystal. The precision is limited by that of the external source. The internal 30 kHz oscillator has an accuracy of plus or minus 50%. This sounds terrible, but this oscillator is intended for use during deep sleep and power-saving modes where the actual clock speed is irrelevant to the function of the code. Last is the hibernation module clock source, which requires an external clock crystal or oscillator. The clock provides the system with a real-time clock source. The system clock, or CPU clock, can be driven by any of the fundamental clocks. The internal 16 MHz main oscillator, the internal 30 kHz oscillator, and the external real-time oscillator. In addition, we have an internal phase lock loop, or PLL, that runs at both 320 or 480 MHz. No, you can't run the CPU at these speeds. Dividers limit you to 120 MHz and below. These 2 PLL speeds are provided so that the integer division is possible for a wide variety of application needs. We also have a divider on the internal 16 MHz oscillator that provides 4 MHz plus or minus 3%. You have 6 different clock sources that can drive the CPU. Only the internal 16 MHz and main oscillators can drive the PLL. This is the Tiva C-Series clock tree. Its flexible implementation provides you with the different types of clocks you need for low power operation, for low cost operation, and for high precision operation. On the previous slide, we looked at the possible sources for the system clock. If you find the system clock line on the right of this diagram and follow it back through the multiplexers, you'll find that any of the 4 fundamental clock sources can drive it. As an example, let's connect a 16 MHz crystal to the inputs of the main oscillator there on the left. You should bear in mind that there are restrictions on the crystal frequency. Working our way to the right, let's also use the PLL, divide it properly to drive the system clock at 120 MHz or below. Making all those selections is simplified with the use of the TivaWare API shown at the bottom of the slide. A single line of code can make all of the choices shown to program the system clock selections. It returns the actual clock frequency that has been programmed. If your selection of PLL and the desired speed are not possible to achieve, the return value may be different from your desired value. You should also be aware that selecting PLL and desired frequencies that result in non-integer divisions can result in sysclock jitter. Tiva C-Series General Purpose I/O is extremely flexible. Any GPIO can be an interrupt, edge triggered on rising, falling, or both. It can be level sensitive to high or low values. Any GPIO can directly initiate an ADC sample sequence or a DMA transfer. The toggle rate can be as high as the CPU clock speed on the advanced high-performance bus. As outputs, the drive strength is programmable to be 2, 4, 8, 10, and 12 milliamps. The 8, 10, and 12 milliamp settings also allow you to configure the slew rate. The GPIO pins have programmable weak pull-up, pull-down, and open drain modes. The pin states can be retained during hibernation mode to correctly connect to external circuitry even while the microcontroller sleeps. The Mux Utility is a graphical interface that allows the user to easily configure the GPIO. Since the pins on Tiva C-Series devices are heavily multiplex, this configuration can be somewhat difficult to do manually. The utility generates human-readable source and header files that can be included in your project regardless of the IDE that you are using. We will often generate the C configuration files and simply cut-paste from them into our code. GPIO address masking is a somewhat unusual technique for programming the GPIO port pins. Each GPIO port has a base address, and if you look in the diagram, GPIO port D has a base address of 0x40058000. You can write an 8-bit value to the port directly to that base address, and all 8 pins of the port will be modified, just like it has been done to GPIO ports since the earliest microcontrollers. If you want to modify specific bits of that port, you would have to read the value from the port pins, change the specific bits, and then write the value back out to the port. This is a read, modify, write operation fraught with issues. For instance, if an interrupt changed a pin state during this process, your code would write the wrong value to the pin. On the Tiva C-Series parts, each port has 256 possible addresses covering every possible combination of the port pins. The GPIO pin write API uses the pin mask and the base address to form the address that allows us to write to the specified pins, in this case pins 1, 2, and 5. We can then write or read from these pins only. You should appreciate that this is not a software masking trick. This technique is completely in the hardware. 6 of the pins on the TM4C 1294 NC PDT have critical functions that are protected from accidental disruption. These are the 4 emulation pins and the 2 pins dedicated to the non-maskable interrupt. Any write to the alternate function select, pull up, pull down, or digital enable registers for these pins will not be stored unless the GPIO lock register has been unlocked. The coding sequence shown uses direct register writes to unlock the GPIO lock feature of port C pin 0. Any read of the GPIO lock register will return it to a locked state. Lab 3 is your first chance to write some real code from a blank page. If you don't understand what a TivaWare API function call does, or what a parameter means, pause the video and look it up in the user's guides. We've provided plenty of explanation in the lab steps, but make sure that you take the time to comprehend what's going on rather than skipping to the solution. Your hard work will be rewarded.